compared to the size of the full moon in the sky. Okay, so we've gone from this tiny patch to a gigantic area, still not so big compared to the full sky, but kind of the size of the full moon. Okay, so it's substantially larger than the original Hubble Deep Field, and the idea is that we want to have more galaxies. Okay, so we want to go from the thousands of galaxies in the previous picture to hundreds of thousands of galaxies, and each one of them would like to observe with every possible telescope. So you can see that this is a monumental task. Okay, it takes a lot of effort, it takes a lot of time. This in particular happens to be the largest HST survey ever undertaken by the Hubble Space Telescope. So it's close to 900 orbits, 1,400 hours over 3 years, observing the same portion in the sky painstakingly. Okay, and all this collaboration, it's only possible because of the team effort of more than 200 people from different institutions. It took a lot of work, and it cost a lot of money to put all these people, all these minds together to really extract information for the hundreds of thousands of galaxies that we have here. Okay, so you can see that as astronomers we need more and more information. We go from the small but very successful Hubble Deep Field into these CANDELS fields where we can get information for more and more galaxies. So now let me go back and try to explain how do we really extract information from observations only. Okay, so what we do is we take pictures of the sky using different filters. Okay, filters like the ones that you can use in your cameras. Okay? So what we do is we put these filters in front of the telescope, and when we take a picture, we only let the light in this color to get through. Okay, so we take pictures with different colors, or to be more precise, at different wavelengths. Okay. Each of these colors have a precise wavelength, so when we create these filters, we only let the light in a given spectral window get into the telescope. So we can check how much light the galaxy is emitting in the kind of blue colors versus how much light the galaxies are emitting in the red colors. Okay? So this gives information about what we call the spectral energy distribution. This is a fancy name to say how much light the galaxy is emitting in the blue versus the red. Okay? So this gray line that you can see here is the spectral energy distribution, or SED, of a galaxy, and you can see that from the gray line essentially that if these are blue colors, short wavelengths, and these are red colors, long wavelengths, there's more light here than here. Okay, so this would be a bluish galaxy. What we do is we take observations in filters. So this is an example with 1, 2, 3, 4, 5 filters. Okay, so we put 1, 2, 3, 4, 5 different filters in the telescope, and we take the same picture again and again. And each picture gives us different information because we're sampling slightly different colors. Okay, so what do we do with that? Okay, so what's going to happen, and you have heard about this, is that because the universe is expanding, the light that is emitted by the galaxies that get to us gets stretched. Okay, so we say that the galaxy is red-shifted. So blue photons get stretched, the wavelength is longer, and following my definition of wavelength and color, the light gets redder. Okay, so even though it was emitted originally by the galaxy as a kind of bluish photon, it gets red. It gets red-shifted. This is what I'm trying to illustrate with this video here. Let me see if it works. There you go. Okay. So I'll let it play and then I'll comment. Okay, so what's happening here is that we have these observations in 5 bands, and we are simulating that the galaxy is moving to higher and higher redshifts. Okay, so it's moving to positions that are farther and farther away from us. So the farther away the galaxy is, the stronger the effect of the redshift. So the stronger is the shift to the red. It's as if you can imagine that the SED, or the spectral energy distribution of the galaxy, is being pulled by someone here. Okay, so you are pulling the light of the galaxy, you are redshifting the light of the galaxy, but your filters are sitting in the same position. Okay? Your filters are always here, but if you observe a galaxy that is at higher redshift, then you are probing different things. So you can see that these points go up and down. So the shape, the orientation, and the location of these points is going to change depending on the distance to the galaxy. Okay? So bottom line, we're just using our probes, our filters, our colors to probe the effect of the redshift into the light that the galaxy is emitting. So the galaxy, it's at higher redshift, so the light gets emitted in redder and redder bands. Okay? So all these can be done with much more detail in large cosmological surveys. So instead of 5 points like the ones that I have in the previous slide, you can have 18. Okay? So in a figure like this, each one of these black points represent an observation taken with a different filter. So if you have enough points for one particular galaxy, you can try to fit that with models that we can create in the lab or in the computer that tell us more or less how much light we expect from the galaxy to be emitted in red or blue colors. We can do this because we can observe, for example, stars around us. We know the temperatures, the colors of the stars around us, and galaxies are made of stars. So we can create our models just by combining light of, let's say, 1 million of stars. Okay? So we can know more or less what kind of light, whether it's bluish or reddish, we would expect for the galaxy. So combining our observation, we can fit that with models, and depending on what the shape of these fit tell us, we can sort of guess the redshift of the galaxy, okay? Because it's going to be something like what I showed in the previous video, okay? So galaxies at different redshifts will have different shapes in this diagram. So when we compare the expected shape with the points that we take with our filters, we can guess the redshift of the galaxy. Okay? We can do a lot more because what we're doing essentially is comparing two models in which we are combining light from, let's say, 1 million stars. Okay, so comparing the flux that we get from the galaxy to the flux that we would expect if the galaxy is, say, made of 100 million suns. Okay, we know how much flux we get from our sun. Let's say we put 100 million suns together. How much flux would you expect? Okay, so we can create expectations and compare that to the observations, and then we can sort of infer or guess not only the redshift, how far the galaxy is, but also how many stars it has or how many stars it's making right now. Okay? This is important because for this we need information at different wavelengths from different parts of the electromagnetic spectrum. Okay? So the bluer kind of UV, optical or near-infrared wavelengths tell us about the stars. Okay? Just like our sun, most of the light comes out in the optical wavelengths. But galaxies are complex. It's not just stars that we have in galaxies. We also have gas because those stars are made of gas. And when stars die in supernova, they eject material into the medium. So there's material, more complex material mixed into the gas. There are dust particles, and those also interact with the light of the stars. So if you go into redder wavelengths, into the radio or in the far infrared, you can see the emission of the dust particles heated by the stars. Okay? So this is all theoretically very complex, but what I want you to take away is that from observations across the whole electromagnetic spectrum, we can get information about the galaxy, okay, without touching it, just making guesses about how many stars would that galaxy have and how the light is emitted depending on whether the galaxy has a lot of stars and gas or whether there is a lot of dust also in the galaxy. So one more important thing that we get in observations is, of course, pictures. So how the galaxies look like. It's not just information about the flux, it's also, do they look spirally, do they look elliptical? And one important thing about candles is that it provides images of galaxies in the near infrared. Okay? This is important because, as you saw a moment ago, galaxies emit different fluxes, or they have different luminosities at different wavelengths. Okay? So some galaxies are very faint in the blue and they're very bright in the red. So on average, the color of that galaxy will be red. So if you try to observe with a filter that is blue, you will get barely any information. So in this case, what I'm showing you here is galaxies. So the first row are images taken by candles in the near infrared, and the second row are the same galaxies observed with a kind of bluish or ultraviolet filter. So you can say that you're taking a picture of the same galaxy and you can see completely different things, okay? And that's because stars are made of galaxies, galaxies are made of stars, and stars emit light in different colors. So some stars are predominantly red. If you try to observe that star or that galaxy with a blue filter, you barely see anything, okay? Instead, if you put a red filter, you see a lot more. Okay? This is important for candles and for high redshift cosmological surveys because of the redshift, okay? So remember just very briefly what I said about the photons getting stretched and getting red. That means that if we are observing a galaxy here and then we take that galaxy at high redshift, all the light of the galaxy is stretched. So the galaxy looks a lot redder. So if I use a red filter, I have a higher chance of seeing that galaxy versus a blue filter because all the light in the blue is actually shifted. All those photons are stretched. Okay? Another way of thinking about this, if you've played with Photoshop, for example, is that when you make a color picture, you're really combining 3 or sometimes more black and white pictures in different bands. So you can see red, green, blue, and you combine these black and white pictures and make a color image. Okay, so if you look at this beautiful galaxy, you can see that it looks kind of yellowish here. There are blue portions and red dots. Imagine that you take a picture with a red filter that can only see the red dots. Okay, you're switching off everything else in the galaxy. You put a red filter, all of a sudden you can only see the red dots of this galaxy. That's the same idea that you have here. Okay, in this filter you can only see the dots. In this other filter, it's maybe working kind of like a combined image. You can see the whole galaxy. Okay, so another way that this effect has is the Christmas tree effect. Okay, you can not see the whole tree, a Christmas tree in the middle of the night, but you can clearly see the light bulbs. Okay, so this is the same thing. Okay, so the red bulbs, the lights here in this band, you can clearly see in one band, but not in the other. And particularly for galaxies that are distant, we need to go into red filters because that gives us more information about the galaxy. And if you want to know the shape of the galaxy, you're better off observing in this band than in this one that you cannot see anything at all. So there's a lot more that you can do with images, of course. We can have your parameters. You just try to chop and slice the galaxy and measure where the galaxy is concentrated, and you're trying to assign numbers. Okay, whether the average light distribution, it's in the center, it's in the outskirts, whether the galaxy is nice and symmetric, where it looks like a disk. So you can make a lot of measurements with just a computer, just like what you would do with any digital picture. But you can also have visual classification. We realized that the human eye is actually very efficient at noticing something like faint tails, companions, defects on the image. So we actually put many of these galaxies, we made postage stamps of the 100,000 galaxies in the Candle survey. We put those online and we asked people to classify, just to tell us where the galaxy looks spiral, elliptical, edge-on, face-on, where it seems like this image has an artifact because maybe there was a cosmic ray or a problem in the image. And it worked fantastically well. So you can go online, you can check Galaxy Zoo. It's a citizen science project, and you can still to this day go online and help us classify this galaxy. Of course, after that, we are also kind of following in the path of this visual classification by starting machine learning algorithms, kind of like the same idea of using machine learning to distinguish between pictures of cats and dogs. Okay, it's the same thing. We're trying to teach neural networks to distinguish between elliptical and spiral galaxies. It's based on the same idea. So all of these are very rich projects that you can do with images from Hubble. Okay, so it's not just the colors, it's not just the flux or the luminosity of the galaxies, it's also the images. Okay, so that's part one. I was trying to describe our observational methods. How do we get information about galaxies? Okay, and now I'm going to talk a little bit about what we learned from those observations. Okay. Remember what I said at the very beginning? I want to know how galaxies grow and form stars. What kind of sizes do we have? Physics behind that is process of gas accretion. Okay, gas gets into the galaxy. Galaxies are essentially big factories that turn gas into stars, and those gas particles are coming into the galaxy with some velocity. They're spinning, so they have some angular momentum. These are all the physical processes that go behind. And what I'd like to talk to you about is observations. What observational evidence do we have for the way in which galaxies make their stars and grow in size? Okay, so let me get started with the star forming sequence. Okay? This is a complicated diagram. There's a lot of information. Let me go step by step. Okay? Firstly, you have your y-axis and your x-axis. Okay? There are 3 panels. They are all kind of identical. The y-axis, you have what we call the star formation rate, which is how many stars the galaxy is making right now. It's a lot. It's not. Okay? It's just a number. Tell me how active the galaxy is. The x-axis is how many stars are already there, okay? In log units, meaning that this is 1 billion stars and this is 1,000 billion stars, okay? So these are very big, massive galaxies with a lot of stars, and we're just trying to answer the question of whether these galaxies are still making more stars than before, okay? So this is a 3D plot. Also, there is color information here. So black, blue, and cyan colors indicate the morphology of the galaxy. So all of these things here in this nice sequence are spirally looking galaxies, okay? They look like this. They have spiral arms. They have kind of yellowish centers and blue arms. Okay? So all of these are galaxies that are still making a lot of stars. They are very active. Versus this thing here, that you can call the death sequence if you like, are galaxies that are not making a lot of stars and they look spiral or spherical. Okay? So there's morphological information and information about the activity. How many stars the galaxy is making, is it active or not? So you can see that then in each of these three panels, what I'm sampling are different epochs of the universe. And I can do this using images from the deep cosmological surveys. Okay? I'm trying to get the redshift and then I'm splitting the galaxies in samples observed at different epochs of the universe. When the universe was very young or when the universe was older. Okay? Closer to what we see around us today. And the first thing that you notice is that this sequence is almost always there. Okay? There's a nice sequence of these key galaxies that are forming a lot of stars. But there's also a kind of death sequence that also exists when the universe was very young. So there were galaxies when the universe was young that were not forming any stars. So for some reason, when the universe was in its infancy, some galaxies were already done. They were not forming any stars anymore. So that's a question that we'll come back to. But the idea is that there's always going to be a sequence here that is what we call the star-forming sequence of spiral star-forming galaxies that are making a lot of stars. Okay. So what we are trying to the way we are trying to explain this sequence is the idea that galaxies will start small, will increase their mass, making more stars, and then they will make more and more stars as they continue to increase their mass. And all of this, try to explain kind of hand-wavingly, is what we call the bathtub model. Okay? So that's the idea that you have your bathtub, you're putting water in, and you're also letting water get out. So the water in this case is gas. You put gas into the galaxy, and then you can make more stars. Those stars explode, some of them die in supernova, so they return gas into the medium. So you're putting gas in, making stars, losing some gas, so it's a cycle. What happens is that when you make more and more stars, the galaxy is more and more massive, so you're increasing the size of the bathtub, so you can feed more and more water. Okay? That kind of explains the sequence here. The more stars you have, the more massive the galaxy is, the more gas the galaxy can pull from the surrounding medium, and then it can make even more stars. Okay? So this would kind of look like a runaway process. You make more and more stars, you can pull more and more gas, and make more and more stars. What's going to happen eventually is that you're going to run out of gas around you, and then that process is going to stop. But while that process lasts, you have this bathtub model, you have galaxies growing in size and making more and more stars. Okay? I think I can illustrate this with this nice video, this simulation from people working on cosmological dark matter simulations in UC Berkeley and Caltech, and it shows just that. Okay? Picture in the center of this video, you have a massive galaxy that is accreting gas. So these green patches here is cold gas that is getting into the galaxy. And it gets into the galaxy just by pure gravity. You have a lot of stars, they are very massive. You have like 10 billion suns there, so it's pulling gas. The gas is getting into the galaxy, it's making new stars, but some of those stars explode. You have supernova, you can also have massive black holes in the center that heat up the gas around that, so you have feedback processes. So green gas is getting in, red gas is getting out, but it's going out into the interstellar medium. It will eventually cool down, radiation, and then it will get back into the galaxy. So you have your bathtub model going in, but the galaxy is getting more and more massive, pulling more and more gas. Until you can imagine that, you see, now these regions are kind of depleted of gas. Okay? So at some point, your supply of gas that starts with a lot of material around you will run out, and then the galaxy will stop making galaxies. So it will stop making new stars. Okay? So one nice thing that we could do with this is that we used models from this video, from this simulation, to try to recreate the star formation history of the galaxy, which is how many stars the galaxy was making when it was young and when it was aging. Okay? And as a result of that, we get these tracks. These magenta tracks shows you what the galaxy was doing when it was younger. Okay? So this shows what the galaxy was doing when it was only 1 gigayear old, so 10 to the 9 years, 1 billion years old, and then where it was when it was 2 gigayears old. So as a function of time, the galaxy is climbing up this sequence, making more and more stars, and then it fluctuates up and down because of these feedback processes. So sometimes the gas comes in, sometimes some supernova explodes, then stops the gas from coming in, then more gas comes in. So it's kind of a stochastic fluctuation, but overall the galaxy gets more and more gas all the time. You can't stop it because the gas around you, it will rain into the galaxy. Okay, so it's getting more and more massive, it will pull more and more gas, it will climb up this sequence until you run out of gas and then eventually you die. Meaning that for the amount of stars that this galaxy has, it's not making new stars anymore. So it will go up, peak, and then go down. Okay? That's the idea of the sequence. So, second scenario, in addition to the star-forming sequence, is what we call the inside-out structural growth. And again, that's a process that you can probably understand better just by looking at this video. Okay? This is the same idea. Now we're zooming in into that galaxy, and this is still the zoom-out picture. Okay? So you have your galaxy in the center of this dark matter halo, and it's grabbing gas from around it. Okay? So the galaxy is becoming more and more massive, and the gas is coming into the center of the galaxy. So you can see when the video starts again that it starts small with a lot of blue things, then gas is appearing, coming in circles, and making the galaxy increase its size. This is based now on observations. Okay, so what I'm showing here on the left are pictures of galaxies from the Kendall survey. Okay, so these are not simulations, even though they kind of look remarkably similar to the simulations that we get from the computer models. And the idea is the same. Okay, you have in the center a lot of stars that are already kind of old, but you are getting more material into the galaxy, spiraling in from the halo around the galaxy. And that material is going to settle in a nice disk, and it's going to form stars. Okay, that's what the gas does. Okay, so you have the gas, it's getting into the galaxy, and when it's dense enough, it's going to start making new stars. And those stars are going to be arranged in spiral arms, making the galaxy larger and larger. Okay, so you're going to have your center where you have a lot of stars that's going to act as the seat. It's a lot of mass pulling gas in, and then the gas is coming in from very different directions. So that's going to give you, on average, some spin for the gas coming into the galaxy. And that gas is going to settle and make new stars around the center. So on average, as a function of time, what's going to happen is that the spiral arms are going to get larger and larger from material coming into the galaxy. Okay? Again, shown in a plot with more quantitative information, what's going to happen is that as the stars are forming, okay, the galaxy has more and more stars, the size of the galaxy is going to increase. Okay? Some galaxies are going to fluctuate a little bit because the way the accretion gets gas into the galaxy is not smooth. Okay? The galaxy can have hiccups. Okay? Sometimes you get a clump of gas, sometimes you get nothing. On average, there is always a positive trend of gas coming in, but it's not a smooth process, as you can see in the video. Okay? Sometimes there is a clump of gas, and sometimes it stops for a little bit. So on average, the galaxy is going to increase its size. Okay? So galaxies, actually I think I have like a summary here. Let's skip the plots for a second, just look at the pictures. I think that's a powerful message. You start, and as a function of time, the galaxy is making more and more stars, typically in a disk that will increase in size. Okay? So these are really galaxies at different epoch of the universe observed with the Kendall survey. The primeval galaxies are tiny. They still have a lot of material in the center. You can see tiny red blips in the center of these things, but the disks are getting larger and larger because the gas is coming in from different directions and helping grow the disk of the galaxy. Okay, so combining these two things in a kind of takeaway message, the idea is that the average, okay, remember what we are doing here is taking thousands of galaxies from a survey and studying all of them. Okay, and we're making assumptions and trying to get results out that represent what on average galaxies do. Okay, so the idea is that on average these star-forming galaxies will increase, growing along a sequence, making more and more stars, and those stars are going to be arranged typically in star-forming disks. Okay, so galaxies become more massive as a function of time, and they also become larger as a function of time, and they typically have these like structures. Okay, that's the average evolution. Okay. Now let me get back to the other question, which is, this is all nice and well, this tells you how galaxies grow, but I mentioned briefly in the previous figures that eventually galaxies die, and you can probably understand that going back to the idea of the video and the gas around the galaxy. At some point you run out of gas, so the galaxy cannot make any new stars. That's what we call death for the galaxies. Okay, so no more gas, no new stars, that means death for the galaxies. So what do we know about that? So this is going to be just the last section of the talk, and I'm going to talk about how galaxies end their lives. Okay. So we go from the average evolution for your star-forming galaxy, and we want to try to understand something else about the galaxies that are not forming stars anymore. And that's going to involve physics like dissipative process, merging of galaxies, and the more important one, running out of gas, running out of material to make stars. Okay, I'm going to describe that from the perspective of two observational features called compaction and quenching of star formation. So, going back to the picture that I showed you before, in this observational graph, you can see that there are some galaxies. So, the x-axis indicates how many stars. Okay, so if you have a billion stars, you can either be dead, so you're not forming many stars, or you can be very active. Okay, and what we think happens is that galaxies grow, they run out of gas, and then they die. But in principle, if what I said is that these galaxies look like a spiral disks, that should mean that they are spiral that grow, and then they disappear and die. And what we found out is that's not really what happened. Okay, so we have to make a lot of quiescent galaxies die in a period of time of roughly 2 gigayears. And sometimes the age of the universe is too short. So when we observe galaxies that live when the universe was only 2 gigayears old, we still find a pile of galaxies that are already dead. So some galaxies have to die very quickly. So maybe those galaxies don't fit the idea of the bathtub model that I mentioned. Those galaxies have to die very quickly because we find dead galaxies when the universe was very young. Remember that I mentioned this a few slides ago. So if that's not a problem, we still have more things, and remember that I said that galaxies on average grow in size. Okay, this is the y-axis again, is size of the galaxy. When you have more stars, you have a larger galaxy, presumably because the disk of the galaxy is larger and larger. Well, it turns out that when we look at dead galaxies at a given mass of stars, so a given number of stars, the galaxies that are there are actually kind of a factor of 2 smaller than the star-forming ones. Okay, so it's not just a matter of running out of gas. If you run out of gas in a spiral galaxy, you still have a spiral galaxy. The size is not changing. But it seems like dead galaxies are actually smaller by a factor of 2 than galaxies that are alive. Okay, so how do we solve that problem? Okay, how do we go from kind of bluish galaxies that are star-forming that have kind of spirally structures and end their lives as these red dots that, for obvious reasons, some people started calling red nuggets. Okay? Galaxies are red, small, featureless, and don't look at all like the star-forming ones. Okay, so how do you get from here to here? Okay, and so the way we try to do this is combine information from the 2 diagrams that I've been showing throughout the talk. And so you have your star-forming sequence. Okay? You have these galaxies that climb up this sequence. They get more massive, they form more stars, and your dead sequence. And as star-forming galaxies make more stars, they become larger and larger, so larger spiral disks. Okay? So if I now draw 2 lines, one here, and try to divide these 2 diagrams in 2 groups, I can then use those lines to create a new diagram. That's what I'm going to do here. So I draw this green line and this dark green line here. So if you are above the dashed green line, you are making a lot of stars. If you are below, you are dead. Okay? So I'm using this line as x-axis here. So if you are above the green line, you are making stars. If you are below the green line, you are not making any stars. And I can also do the same thing with the size. Okay? So I now have the dark line that is going to become the y-axis. So either you are above the dashed line and you are large, or you are below the dashed line and you are small. Okay? So if you are on the left side of this diagram, you are big. If you are on the right side of this diagram, you are small. Okay? So I can combine the information on how active you are and how big or small you are. And now the question is, if you are star-forming, you are big. You are on this side in both diagrams. If you are quiescent, if you are dead, you are small. So how do you get there? Do you shrink in size and then you die? Or do you die and then you shrink? Okay. So we're just trying to split the diagram into a new diagram that we can check observationally. Okay. So that's what we do. Now we make this diagram with real observations, trying to find the story. Okay. If most galaxies are here, that means that star-forming galaxies have to shrink first and then stop forming stars. If they are down there, that means that they stop forming stars and then somehow shrink. Okay. And the answer to that question seems to be that most galaxies become small before quenching star formation. So they have what we call compaction process. They will go from large star-forming disks to small and round star-forming galaxies, and then will stop forming stars. Okay, so this is the new diagram that I'm making with the y and x-axis, and it's based on this. Okay, so it's based on this star formation versus mass and size versus mass diagram. The postage stamps of real galaxies here in green are these green dots. Okay, these galaxies are on the star-forming sequence, so they are massive and they're making a lot of stars. But when you look at these green dots on the size versus mass diagram, they are as small as the dead things. Okay, instead of being large disks, they are round red things. Actually, they look remarkably similar. Okay, if I only show you the postage stamp, it is very hard to tell whether this is dead and this is alive, or vice versa, because they look essentially the same. And that's because you're only looking at the color picture. Okay? What's happening here, and I'll talk about that in the last few slides, is that these galaxies are red because all of their stars are old, and typically all the stars emit more light in the red, whereas these galaxies are very red because they have a lot of dust. So a lot of dust is in front of the galaxy and our line of observation, so all of the blue light from the young stars is being absorbed by the dust and re-emitted in the red light. So they look remarkably similar, but they are widely different in terms of star formation. Okay? These are very active, these are dead. Okay? So how do you make a really tiny galaxy like this red nugget out of a big galaxy? Okay? So theories tell us that's possible when you have mergers of galaxies. Okay? And we have pictures in the local universe of galaxies that are merging. What's going to happen is that these galaxies are going to spiral around each other, they're going to get closer, they're going to trigger compressed gas on both galaxies, make a lot of new stars, and then they're going to coalesce. Okay? So the big massive centers of the two galaxies are going to eventually merge with each other, coalesce, and then the rest of the material is going to slowly fall into the new massive center. But that still, takes a lot of time. Okay? So merging galaxies is an efficient way of taking two big things and making something small, but it takes a lot of time. We need something else that can happen faster. Okay, so another way of getting that our friends in the theory and simulations department tell us is that galaxies can have hydrodynamical instabilities. Okay, so that's a big word, but looking at the video again, I think the picture is clear. So you have a big, massive seed in the center of a simulation, and then you have a lot of gas raining into the galaxy from different directions. Okay, so this is not a smooth accretion. You don't have a pipe and then gas come in and you make stars. Okay, this is gas raining into the galaxy from different directions, like you see here. Okay, sometimes you have clamps. The accretion can be episodic. You can make clamps that become gravitationally stable and then are getting dragged into the center very quickly. You can form accretion lines that are kind of like expressway entrance into the center of the galaxy. So instead of spiraling in slowly, they just go drag into the center very quickly. Okay? And then you can have some of the clamps also spiral in and then merge into the center. And when you put a lot of gas together in the center of the galaxy, it explodes. Boom. Okay? So you make a lot of stars very quickly. And that's where we are trying to look for observationally to confirm this model. Okay? So we are trying to find galaxies in which a lot of the gas is going to spiral into the center and they're going to have what we call starburst. Okay? It's not just a spiral galaxy making stars quietly, quote unquote, in the spiral arms. It's just a lot of gas being dumped into the center of the galaxy, making stars very quickly in a very short period of time. Okay? So after that happens, there's going to leave a blank empty space in the center of the galaxy where all the gas was consumed. Okay? So this tells you that all of the gas is going to be consumed very quickly, and after that you're going to run out of gas and stop. So this is the galaxy is going out with a bang. Okay? Instead of consuming the gas smoothly for a long period of time, spreading the stars around in a nice disk, all of the gas gets into the center, it explodes, makes a lot of stars in a very dense region, and then it's done. Okay? It's a different picture. And we compare this with simulations and how that evolution would look like in a size versus mass diagram. And what happens is that galaxies will go from a phase A, these orange dots, in which they actually look like, kind of like spiral disks with some clamps, and they have these gravitational instabilities, and all of the gas is being dragged into the center. And the galaxy now is making a lot of stars, but only in a very small region of the galaxy in the center. Okay, so what happens mostly is that all of the gas is being redistributed very quickly into the center. So the last batch of stars is formed only in a very dense region in the center of the galaxy with a big explosion. So in terms of visual appearance, it changes dramatically. Okay? And not only that, it also consumes a lot of gas. So it fits into the idea that after you are done with that, you do that very quickly and then you're done. So you go into the pile of red nuggets. Okay? So you solve both problems at the same time. Now, question is, all of this is very nice in simulations. Can we see that happening? And the answer is yes. Okay? We can go and observe one of these red nuggets that are not dead. They are making a lot of stars, and we can tell that there is also a lot of dust that is obscuring the light emitted in the blue. Okay? This is like the picture that I was showing at the very beginning. This galaxy is trying to emit light in the blue wavelengths because young stars emit light in the blue. But there's a lot of dust in between eating that light, so that light never gets to us. In return, what we see is a lot of red light. And if you remember, I also mentioned that what happens with the dust is that after getting all that energy from the young stars, it's being heated, okay? So you're heating the dust, so you're moving the dust faster, so it's like an ideal gas inside the box, okay? So just providing more kinetic energy, the dust is getting hotter, and it's gonna radiate all that energy into the radio and the far infrared. The problem is that we don't have nice high-resolution telescopes like Hubble in the far infrared, so when you take a picture with Hubble, it looks like this, very nice high-resolution, and this square here is this tiny little square here, okay? So you can zoom in and you see this red dot. If you take a picture of this area with an infrared telescope, it looks like that. It is horrible, okay? It has a much poorer resolution. So we cannot guess that this black dot here is this galaxy, but it could actually be any of these things, okay? A way around this problem is instead of using space far infrared observatories, we can actually use an array of antennas from the ground that can actually span to make a 50-kilometer array. So we can combine not only the flux but also the positional information to create a high resolution image based on interferometry. Okay, different technique, but it allows us to actually create a high resolution image. So instead of this horrible far infrared blur image, we can actually make a very high resolution image with this array of antennas called ALMA, and what we can see is this thing. Okay. So this is the same. Okay, this red star here is information coming from the array of antennas, okay? And now it has even better resolution than Hubble. So this black contour here is what you see in Hubble using candles images, and you actually see that all of the far infrared information, all of the flux emitted in the red photons is coming only from the center. So you really have a wild burst of star formation in the center of the galaxy that is obscuring a lot of the light, but all of the dust is really in the center of the galaxy. Okay? So you really have a burst, and that burst is in the center of the galaxy. So this idea would be consistent with this model of compaction, in which the gas is somehow gravitationally unstable and it gets dumped into the center of the galaxy. So if this galaxy were to continue forming stars only in the center as a function of time, what would happen is that in any of these diagrams showing size versus mass, the galaxy will obviously move to the right because it's making new stars, but the galaxy is actually becoming smaller. Okay, so remember the previous slides in which I was trying to convince you that galaxies, spiral galaxies, get larger. These actually are going to shrink because most of the stars, or most of the new stars, are being formed only in the center as opposed to in the outskirts of the spiral disk. Okay, so sudden change in the distribution of gas and where the new stars are going to form. Okay, so let me then conclude. I think I have 5 more minutes to wrap this up and try to hopefully provide the last evidence into this model and sort of continue with the story that I'm trying to tell you. We start with disks that are growing in mass, so they're making more stars and growing in size. Some of them, in one of these episodic events of accretion, can have a hiccup, okay? Can have a compaction event in which they cannot process all the gas that is raining into the galaxy, and all of that collapses. And instead of making a nice spiral disk, everything gets dumped into the center and you make a gigantic starburst, and you make a red nugget, okay? You make a very compact, dense, small galaxy. But do you really run out of gas or not? Okay, that's a problem that we still don't know how to answer, because that requires understanding how gas is distributed around the galaxies. And this gas is not glowing. So we take pictures of the galaxies, but we don't see the gas. So we don't really know if this galaxy does not have any gas around it. Okay, so that's a hard question. What we try to do is trying to understand whether this galaxy is going to stop forming stars very quickly or not. Okay, so instead of observing this galaxy, we're going to observe another one in between this line, because the moment we think this galaxy crosses the line, we'll go from the star forming sample into the quiescent sample. Okay, so we do that in this, again, diagram, in which what I'm doing is showing distance from this dashed line. So either you are above and you are star forming, or you are below and you are dead. Now this is a horizontal line here. If you're in the star forming sequence, you are in this line. If you are dead, then you drop and go into the quench region. Okay, what we're trying to answer is whether these galaxies run out of gas, and then instead of slowly quenching, okay, so running out of gas in a nice spiral arm, they actually consume everything very quickly and then essentially drop dead. Okay, so they are here close to the sequence. We are guessing that they are going to consume everything and drop dead. Okay, so straight line if you like. Or whether they are then rebuild the disk, for example, and continue growing in size. Okay, to answer that, again, it's a complicated process. I'm just trying to summarize everything in one slide, but the idea is that you get additional information that tells you about long time scale and short time scale of the galaxies. Okay, so when galaxies age, their spectrum, so the light that they emit, gets redder. Okay, so by sampling something like blue versus red color, we can put that into the x-axis, and we know that the galaxies are aging. But we also need something that is called a short time scale indicator that tells us about how fast the galaxy is dying. How do we do this? We check for lines in the spectrum of galaxies. In this case, these are absorption lines that form only in the atmosphere of stars that are relatively young, but not so much. And what happens when you make a lot of stars is that the big stars are shiny and gigantic. So all the light that we get here, it's outshined by the emission of the gigantic stars. When those stars die, you can see the next generation of stars, and that next generation has this spectral feature. Okay, so the fact that you can see this spectral feature means that the big ones, the ones that you should have if you are making stars all the time, okay, because whenever you make new stars, you have to make some of the big ones. Okay, so if you're still making new ones, you should have some of the big ones, and if they are there, you cannot see these. So the fact that you can see this on the galaxy means that the really big ones are not there anymore. So you stop making those stars. And that's a short time scale indicator that we are finding in some of these galaxies. Okay? So those stars will also die. So that's why in this diagram you have a hump. You can see this line for a short period of time, and then the line will disappear. So if you find galaxies in that stage, you can sort of infer that the galaxies stop making new stars some time ago that is not very far into their past. Okay, so connecting it with the diagram that I was trying to show you before, now I'm putting observations of real galaxies, and it's just 4 galaxies. We are hoping to do a lot better and more clear when we have James Webb flying, and we can take spectra of thousands of these galaxies to look for this signature. But the idea is that this suggests that these are galaxies that are dropping dead from the star forming sequence, so they stop forming stars very quickly because presumably they ran out of gas. Okay, so summary of this, and just to wrap up, I think it fits the idea of live fast and die small. Okay, so instead of live slowly, happily ever after, just creating more gas, growing your disk, making a beautiful spiral galaxies, which by the way exist because we see them around us. Some of them are actually not going to go that route. Okay, they're going to live fast. All of that gas, it's not going to be spent in thousands of years making a spiral disk. It's just swept into the center very quickly. They're going to make a big bulge, massive center, and then they're going to run out of gas and die as very small things. Okay, so just summary of the summary, putting all together in a nice picture, combining what I said at the beginning with what I'm saying right now is just you can live in this nice sequence, getting gas, and then having feedback processes, so running out of gas, and then getting yet more gas from the halo, and then you can live up, up, down in this star-forming sequence for a long period of time, making a large disk. Or maybe in one of these processes, you take too much, and all of that gas gets swept into the center. That's more than the galaxy can really digest, and they die in a gigantic starburst, making a very small and compact thing. That's the end of their lives. So, combined with the idea of the galaxies, if you remember, I showed you this a few slides ago. So this is the inside-out star-forming sequence of nice spiral disks. So on average, many galaxies go this route. They grow, they have nice red centers with a lot of stars, but they also make a lot of new stars around. And the disks grow, 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 and they continue to get larger. Some of them, something goes off, something goes wrong in some point in their lives. A lot of gas stops being distributed in the disk, and it goes directly into the center. So they only make a big, gigantic center, and they drop dead. Okay. And this can happen at any point. We have a long discussion about that. The likelihood of this happening really depends on how gas-rich the universe is, and that really changes as a function of time. But that's a story for another day. This is the short overview of whether you can live a long, quiet life, or you can live fast and die small. Okay, and I'll leave it at that. Thank you.
We had a model. I mean, it's more of a comment, and I think that's why I wanted to say this. We had a model of galaxy evolution, and that goes all the way back to Hubble not really understanding the sequence of morphological types. We have work that was sort of saying, look at all of these events that happen in the life cycle of a star related to its central supermassive black hole, the AGN sequence. I'd like to just say how impressive this work is to really add and have a whole new model, and I'm going to kind of ask it only as one question, because I'm hearing this as a way to sort of generate however we want to call them, but the red, the quiescent galaxies, we're generating them from the elliptical itself, not through the model that we had of cataclysmic mergers to redistribute the gases. And so I find this, I mean, just tremendously interesting. And what would you say is the current state of that? Are you saying that this is the dominant form of the death of a spiral into an elliptical type galaxy, or at least a red or quiescent type, is through this compaction and the dominant spheroidal, a ball-shaped component in the center because of one sort of starburst event? I might be mixing a few words there, but clearly a starburst type event when you're having this compaction in this general.
So all this is connected, and by the way, in the last slide you probably saw that it's simplified with the parentheses. So this is kind of the general talk. I'm trying to describe a model that sort of does everything, but of course we still don't know a lot of things of how this happens. So this is just a model that we think works for some galaxy, but it's hard to describe. It's not like we got galaxy evolution solved, done and done. I can quit my job and do something else. This is just the beginning with formation of these very red, tiny little galaxies. And it all goes in connection with this picture here, right? So we can see the galaxy, but what we see when we take these pictures is really a tiny portion over there. There's a lot going on that we know happens, mostly based on simulations, but also observations of gas around galaxies. And we know there's a lot of gas around galaxies. So if there is a lot of gas raining into the galaxy and the galaxy still doesn't have a fully settled disk, the chances of the galaxy collapsing on itself are higher. So there's a higher chance of making very red compact galaxies very early on in the history of the universe. You of course have, and you have some of the other ones in which you just have some very nice and large spiral disks that are going to collide and essentially smash each other and make a very big fat center. But those will, and they're fantastic pictures. I don't think I have any with me right now, but people are taking pictures of gigantic ellipticals in the local universe with very wide cameras, so very wide angle, and you can see still tails of very faint material distributed around this nice spherical center of the galaxy. So you can see signatures of major mergers in galaxies in the local universe. We think this is the route that early galaxies in the high redshift universe, when pretty much everything was gas rich. Okay, so all of this gas is essentially left over from the Big Bang. So whenever the universe was cool enough, you start to make a lot of hydrogen, and it's just uniformly distributed around galaxies. So it's right there for the galaxies to take and make stars. And sometimes it's just too much. They cannot take it in. They cannot redistribute the gas in an orderly fashion, and they just collapse and make very dense red nuggets.
That's fascinating. Now, I did promise everyone, if you do need to take a moment to get out quickly and quietly.
Greetings, wonderful presentation of the way. I was just curious, so given this general model of galaxy evolution, I think I'll ask a question slightly more closer to home. Where does our galaxy fit on the current horizon of expected galaxy evolution according to your model?
I think, and this, believe it or not, is a question that people ask frequently in our conferences, because it's hard to put, we don't really see the whole galaxy, our own galaxy, so it's hard to put an exact point in this diagram, but I think it's close to that, but still spirally. So our galaxy is not going to follow this model of becoming small before quenching. Some of the galaxies will just slowly die running out of gas. So they will live the quiet life. Our galaxy is like that. It's a spiral galaxy. It probably formed slowly climbing up the sequence. Now it's relatively massive. It's probably going down. So our galaxy is still forming stars in the spiral arms, but more quietly than it was a million years ago. So it's slowly going down. So it's somewhere here in the transition. I think most people still call it a star-forming galaxy, but it's near the edge. So it's definitely slowing down.
That's interesting, thank you.
The place of dark energy and the expansion speeding up, does that fit into this picture? Or no?
It does. It has to, because all the information that we get, I mean, the very basic, the bare bones of my talk started with observational effects and the redshift. Without the redshift, that is essentially caused by expansion and that dark energy, we cannot do any of this. So all of these results are based on observations with of the CMB, with COBE and Planck and many other satellites. So we need that to solidify our understanding of the cosmology. So it plays a role in the cosmology, in our observations, but I have to say that for galaxy formation, what happens is that all happens in a very small scale where the effects of gravity dominate. So the space around these galaxies is not expanding fast. It's just between us and this galaxy, there is a lot of space. That space in between is getting stretched. So we see that redshift happening. But around a given galaxy, we basically reject or ignore all the effects of dark energy. So the space around a given galaxy, the density of dark energy is small compared to the density of real matter. It's just the distance between us and the galaxy is gigantic. So in that space, the density of dark energy is a lot larger than the density of real matter. And then those effects dominate. Go ahead.
In your diagram, the bathtub model diagram, the halo that's around it, is that just the effect of gravity directly around it, or is that the dark matter halo?
It is both. It is both. So going back to the previous question of cosmology, the only way you can get this started is you have dark matter at the very beginning. So it didn't play an important role in my talk, but you really need that as a beginning. So when I show a video like this, there's a galaxy in the center, but it's really a dark matter halo in the center. So dark matter halos are really the seed in which material starts to fall in, and then you form the first galaxy, the first stars, and then everything else follows, kind of in a runaway process. So you make more stars, more gas, more stars, and then it all goes exponentially increasing, because I didn't mention this, but all of these diagrams are actually logarithmic. So it's a very fast process, but it all started with the dark matter halo. So this really, and I think it shows actually on the picture. I probably didn't do justice to all these things, but this is the halo. Okay. So the halo is there. What's going to happen is that at the beginning, the ratio of regular matter to dark matter in the halo is kind of smooth. It's homogeneous. The moment you make a galaxy, the center gets a lot of baryonic material. So the amount of real matter to dark matter in the center is a lot larger. So at that point, you kind of, again, ignore things. So dark matter does not play a role in the center of this galaxy forming, but it controls everything that happens. So gas is getting in these filaments because of the distribution of dark matter. Go ahead.
On one of your first graphs where you had the video with the 5 points that were moving to the left, your vertical axis had flux, and
Correct.
The other was wavelength.
Correct.
As time went forward, the amount of flux decreased. Is that correct? Because the points, they rise and then decline, right?
So what's really happening is that I got this video from a nice page I thought that illustrates a lot of things, but what we should really have here is this figure extended, because what I'm really doing, and I was trying to illustrate this with the board, that is that this gray line is moving to the right. It's not going anywhere. So it's not that the flux is decreasing, so nothing changes on the galaxy. It changes in our observations of the galaxy. So if this galaxy is at this redshift, this is what we see. If now you put this galaxy at a higher redshift, the galaxy is still the same. It's just all the light that the galaxy is emitting gets a lot of stretching between us and the galaxy. So when we see it, you actually see another portion of the light emitted by the galaxy. So the galaxy emits this and something that you're not seeing in this figure. So if I could show you the whole x-axis, you will see that the SCD of the galaxy goes up and then down. So there is something here that bends down. And when I move the galaxy to high redshift, I just push the galaxy. So it appears in this window, but it's just really moving. So it's the same thing. The spectrum is now here. It's just you don't see it.
Okay.
But what we are doing is just pushing the galaxy. And it shows you how the observations change. The galaxy is not changing, your filters are not changing, it's just the distance to you, between you and the galaxy is changing. That's causing this observational effect. Okay?
So, one of the slides you showed on the age of the galaxy observed different points of the age of the universe.
Yes.
But the question that comes to my mind, not this one, the previous one, I guess, is how you know you're following one galaxy at all times as you zoom in, if you will, to observe different ages of that particular galaxy. How do you know it's the same galaxy?
It is not. So you cannot follow one galaxy in time. So what you do is follow multiple galaxies in multiple epochs of the universe and say they're kind of the same family. So this one is going to behave like the other one. You cannot follow one galaxy. You observe one galaxy, and if you observe that galaxy 10 years from now, it's going to be the same. Same picture in the same spot. You cannot even see the galaxy rotating or anything like that, because it takes place over time scales that are too long compared to the life of a human being. So you are done. You observe one galaxy, you're stuck with those properties for that particular galaxy forever. But you can observe thousands of them. And they actually, I didn't show anything like that, but I mean, this diagram could be something like that. When you observe them together, each one of them is different. They don't look exactly the same. But all of them are kind of disky, so we mash them together into star-forming subset. And we are saying, more or less, they all have the same properties. It's not true. There is going to be a spread. So for a given number of stars, some of them form a few more stars, some of them form a few fewer stars. But on average, we're trying to do statistics of large numbers.
Thank you.
So you said you had an 18-point model for
Right.
sort of, doing 18, sorry, a photometry with 18 different
Right.
bands.
This one here.
Did you go back and, I'm just curious about how the process works of sort of verifying that that's working properly. Did you go back and check spectral lines too?
I think I put one at the very end just to show how the scale of these things. So I'm just showing the nice results, but really doing all this work. Alright, so this is this. Okay. So this is a region in the sky, and these are some of the 18 different pictures that you are taking. So this is the galaxy you observe in this band, this band, this band. They all have different resolutions. They all have different sensitivities. So there's an enormous job to put a diagram like this together. So all of these dots come from all of these images. But people observe these images over years with different telescopes. So there's a lot of work in just making sure that the fluxes are correctly calibrated in the same system, that you put them together. So it's not just, that's your galaxy, you have 18 points. It's a lot of work. You can see the brutal difference in resolution between some of the bands. So it takes a lot of work, but people have been doing this for a long time. And there are gigantic teams putting their minds together to do this, so that we can just show this and say that life is easy.
If I could ask a follow-up on that, and it's just the technical. So, you know, in terms of precision of the photometric redshift from this, you know, these look like much higher precision
Yes.
photometric redshifts than I'm used to. We're just looking for a dropout, or, you know. So, what would you say in terms of fractions of, z, what
Yes.
are the,
So people are really doing this now, in which that they're really studying, and this is going to be important for surveys that are going to be sampling the whole sky several times every night, and they are going to use a lot of filters to try to guess the redshift. So in the old days, people would do this just with one filter. I think I have this thing over here is an example of a dropout. So if you look at this image, you don't see anything there, but I think if I change that, is it moving? I think I made a video. Okay, so it's this slightly lower resolution, but also a different band. So all of a sudden you see something there that it wasn't there before. Okay, this is the dropout technique. So it was essentially two images. Oh, something is there, so it must be a high redshift, because if it were a lower redshift, you would still see the light in the blue band. That was the beginning of the estimating redshift with just points. Now you can get 18, sometimes 40, and sometimes spectroscopy. So you can combine photometry and spectroscopy. I don't think I mentioned this, but you can make these observations better and better and adding more and more information. So it was at the very beginning. So this one is 18 points. This is 18 points, and you can see a lot of points here. Okay? So this is from a GRISM in the Hubble Space Telescope. So the Hubble Space Telescope takes not only images in a given band, it can take kind of a spectrum with the GRISM. So it's a low resolution spectrum, but it gives you the equivalent to 40 more points. So you have 18 bands and then kind of 40 more in just that region, more densely sampled. That's fantastic for the redshift resolution. But still, I think this here is the probability distribution of the redshift. So the peak is kind of still puffy, but you know it's not a galaxy at redshift 1. It's definitely 2 point something. So good enough, not perfect.
that inset there then
It's
is
the
a probability.
Correct.
Got it, okay. Okay, I think we have time for one more. It would have to be a kind of quick question. Yes, Shannon.
So, if I recall correctly, you said that the amount of galaxies that live fast and then just drop dead was a lot higher at the beginning of the universe. Why was that?
It's because of the gas. So we think that happens because of gravitational instability. So what happens is that the primordial galaxy is just a tiny thing with some mass, and then it's trying to accrete material that will fall swirl in with some angular momentum, so it's spinning. But the disk is not fully settled, so you don't really have material to just drive the gas like a pipeline. Okay, so it's raining into the galaxy. Really, when you look at this video, you can actually get cubes of this and look at the galaxy in different directions, and you see it's really raining from different directions. So in the end, it's more than the galaxy can take dynamically. So the forces are not really balanced, and sometimes it just falls into the center very quickly. It's really hard to explain with math. I've seen like models of this and papers of this, but it's really beautiful to understand it in videos like this, because you can really see all the material coming into the galaxy from different angles.
Well, let's thank our speaker. That's fantastic.